slopes with lines on pressure temperature phase diagrams. In case of water, we mentioned particularly interesting about the negative slope of this fusion line, which is nearly a straight line. Well, that's really straight. It goes up pretty steeply. So as you can see here on the insert, which is shown to scale, it goes up pretty fast. And the exact Clapeyron equation will be written in this notation. And if we know the heat of vaporization of water, which we know, and the change in volume of water on freezing, which we know, and the heat of freezing point, which we know, we can calculate that slope. So that's the first order of business. So here I've done this, so we'll have to write it out. Right now, the equation state for the fusion process. These are experimental values of the heat of fusion, about 6 kilojoules per mole. The change in volume is negative, about 1.63 milliliters per mole, about 9%. That's the reason that we were careless about allowing water to freeze in controlled environments. There can be damage. You don't have antifreeze in your car, engine block, your radiator, freezes, it's going to break that block open because of that tremendous amount of force. The volume changes by that amount. Well, here was the exact Clapeyron equation. Of course, if it's delta H over T delta V, it's also delta H molar over T delta V molar. So just writing those numbers up there, jot down. And we get minus 133 atmospheres per Kelvin. That's a pretty steep negative upward slope. I mentioned here that we can also calculate the fusion, the delta S of fusion for that same process. And it's just Q reversible over T. Q reversible is delta H of fusion. Delta H over T is about 22 joules per K per mole. Include that because it's important to know how to do that equation, because I want to refer back to that number a little later. Lecture in another context. So a special case of the Clapeyron equation for evaporations, vaporization, is not exact, but an approximate equation. And you can judge the quality of the approximations as I write them down. In evaporation, one phase always is a vapor phase, a gaseous phase, and so let's let the vapor be an ideal gas, always easy, always tedious to put in all those equation state parameters around what the mathematics required to do the follow-up processes. So let it be an ideal gas. Then delta V of vaporization just becomes the vapor of the gas minus vapor of the condensed phase. That's true with dark, so it's an ideal gas, so we make it an ideal gas. That's that. So that's one approximation. The next is to assume that the vapor of the gas is so much bigger than the vapor in the condensed state that we can neglect that one and say that delta V vaporization is approximately the volume of the gas. And of course it's an ideal gas, so that's nRT over P. When we make those approximations, the Clapeyron equation, change in pressure is effective temperature under saturated conditions or equilibrium conditions, phase equilibrium conditions. Then goes to approximately delta HV over T times delta V. Now delta V we replace by nRT over P. So this is just delta H vaporization over number of moles over RT squared and P up here. So we can write it out as approximately delta H molar of vaporization times pressure over RT squared. Or we can write it as dP over P is approximately delta H molar vaporization over RT squared. Or we can write it d logarithm of P is approximately delta H over RT squared times the derivative of what? Minus 1 over T. Differentiate minus 1 over T, you get 1 over T squared plus 1 over T squared. So we have reiterate that the logarithm of vapor pressure is about minus delta H over R times the derivative. How about that? Minus delta H over RT plus a constant. We can write the vapor pressure itself, that is about E to the minus delta H vaporization over RT times a constant. And this, to me, looks very much like a what? What did I tell you to be on the lookout for in your study of physical science? Boltzmann factors, okay? Just like the Boltzmann factor. In fact, it is. Just to say that the vapor pressure of material, to the extent that the vapor behaves ideally, follows Boltzmann statistics. Indeed it does. We can go back to that statement where we had the logarithm of the vapor pressure was minus RT minus delta H RT plus a constant, and plot that, take measurements, plot the logarithm of the vapor pressure versus 1 over T, and we should have a straight line of which the slope is equal to minus the heat of vaporization over the gas law constant. Now, using that method to measure the vapor pressure, the vaporization of water, we find it's about 41 kilojoules per mole. And if we compare that to the heat of fusion, which was much less, the reason for that is that it's a lot harder to separate molecules completely from the, if they have one another into the gaseous state, than it is to nudge them away from the locked-in position of the crystal to the looser position liquid phase, taking much energy to melt as opposed to evaporate. So for water, we had these results. We see our spot of LH of fusion, delta S of fusion, you see delta H for vaporization. We can also write delta S of vaporization. And this was 6.01 kilojoules per mole. This was about 22 joules per mole. This vaporization we just found long ago was 41 kilojoules per mole. And you divide that through by what? This would be equal to delta H vaporization divided by
Temperature.
the known boiling point. Let's do that. 373 Kelvin, we get 109.9 joules per Kelvin. Notice that the entropy of vaporization is much greater than the entropy of fusion. So I leave this topic with a suggestion that
Should per
we
Kelvin
look
mole.
at, yes,
The entropy units you've got there for delta SF, should that be joules per Kelvin mole?
yeah, joules per mole.
And then the
So-
first
The
one there?
second.
Yeah,
Yeah,
they're all molar values.
yeah, that'll be K mole per K mole.
Joules per mole per Kelvin. Okay? So here's a little problem you can work on at your leisure. Estimate the boiling point of water on a mountaintop at 3,000 meters. We know delta H vaporization. This is 41 kilojoules per mole. We know that the normal boiling point of water at 373 Kelvin. That is that. Take, let's see, the average or molecular weight of air, 29 kilograms per mole. And take as an average temperature of air over that elevation, the bottom top of that mountain is about 20 degrees Celsius or 293 Kelvin. And then recall the isothermal barometric formula, which we could derive back from the study kinetic theory. Was that the air pressure at height H relative to the reference pressure zero, zero elevation, goes to E to the minus this average molecular weight of air times acceleration of gravity times H to the R times this average temperature. So that was the result that we obtained back then. We could say that the H of E0 E to the minus and now, using the Clausius-Clapeyron equation, P2, which is same as pH, P1, same as P0, this equal to what? And the E is minus, what did we see back there? It's delta H over vaporization over R E. And this is RT of the air, this is where I'm going to put that. Now, this exponent and that exponent have to be the same. It's the pressures at the top of the mountain, bottom of the mountain are the same in these two equations. So I'm just asking you to show that this reduces to 1 over the boiling point at H top of the mountain minus 1 over the normal boiling point, which is 373 Kelvin, is equal to the average molar mass of air times G times H over LH vaporization times this average temperature of air. Solve for solve for PV H and delta PV, and this one is about 363.4 Kelvin. This one is about minus 9.6 degrees Celsius. Now, all students of chemistry need to be able to do this. I'm putting this in to show you that we've laid the foundation for doing it, because all these equations can be derived. And also sort of show some connectivity from the work we did earlier in the term to what we're considering now. But if you're worried, I have to do this on the test on Friday, actually, no, I didn't put that problem on the test. I thought about it, but I thought I got that problem. We got that problem. So I didn't put it on there. But nonetheless, at your leisure, sometime before you graduate, work that out. Get yourself do that. Now, another reason I did this is this decrease in pressure here is about 10 degrees. Maybe temperature about 10 degrees going up and down. Reminds me to tell you that we will learn, I hope, sometime before the end of the term, when we're talking about reaction kinetics, that for the typical garden variety run-of-the-mill organic reactions involving ordinary molecules like rule of thumb is that if you change the temperature by 10 degrees Celsius, you about double or halve, depending on which way you're changing the temperature, to the reaction rate. That's not accurate, but it's close, and we'll see why that is. So, if you go into the mountain and you bother to carry a fresh egg all the way up there, you want to boil for your breakfast. Climb out of that cold tent in the morning, and you're used to having a 4-minute egg, better boil that sucker about 8 minutes. It takes that long to do the reaction at that lower temperature. Now for that, let's remind ourselves that for
Could you slide the paper down, Professor?
is it there now?
Yep.
For change in state, constant pressure and temperature, U is equal to QP equals delta H. And that's equal to summation of UI, HI bar. And the driving force for spontaneous change is proportional to minus delta G. Minus delta G is equal to minus the summation of UI, GI bar, but we have another name for GI bar, that's minus UI what? What's the other name for it?
Chemistry. Chemical potential.
UI.
Use your brain.
Chemical potential. UI. Partial derivative of G, respect to Fi, FP, E, Now we tabulate values of HIs or HI0, we tabulate enthalpies at some standard, arbitrarily chosen standard conditions. And we tabulate the heat capacities as well. The arbitrary choices we make are for each element that the standard molar enthalpy, each element in its most stable state at the standard conditions, its enthalpy is 0. And the gases behave as ideal gases. And that the standard enthalpy for elements or compounds, for elements in other than their standard state, most stable state, and compounds under any state is equal to the change in enthalpy on the formation of the element of the compound from its element at the 0 enthalpy standard state. And we found that typically this is equal to delta H on formation from the elements. Now, we explored the utility of that. I wish to do the same for EI0, which is the GI bar, which is GI molar for what? With your substitution. Well, so we choose the same standard space as for enthalpies. I won't repeat all that. Each element, each element in its most stable state at our standard pressure and temperature, 1 bar, 1 atmosphere, 25 Celsius usually, is assigned a value 0 for enthalpy and for chemical potential. We can't measure the enthalpies absolutely, and since free energy is H minus TS, it's got H in there, we can't measure that absolutely, we can't measure free energy absolutely. So we have to do it wrong. We use the same arbitrary choice as we did for enthalpies. So what we hope to do is to have our substances. We've got H other substance. This is equal to delta G zero formation from the elements. You can do like teach vocabulary about this stuff. And we have for any element in a stable state, no stable state, at D0, D0, this is 0, and this is 0. For example, the hydrogen ideal gas, that we over here, 0, and that's a 0. Oxygen gas, 0, 0, 7. Now, we put things like water, liquid in here, we had a minus 285.83. Already put that. Carbon dioxide, a minus 393, what we put there. We also had H plus, aqueous. We had to allow for charges, electrolytic processes. We assign that an arbitrary 0. What we do, we'll do this in here. But this and other interesting entries we need to find out where they come from, how we get them, what they are. How do you determine U0 or other substances such as compounds and so on? Well, one way we already know about. We talked about free energies the other day. We talked about harnessing free energy to do work, and we saw how you can do that with a chemical reactor. That's a good way to get this information. There's another chemical cell for which the free energy was minus delta G, for which delta G is equal to minus N FE. Delta G0 is equal to minus N FE0 for the cell. That's EMF of the cell. When all the reactants are in their standard states. Let's look at an illustration. Rather than try to draw this all out up here, take time to do it. I just went to the way it popped out some. Made it generic hydrogen oxygen fuel cell. You just imagine the cell has these features. A supply of hydrogen, that's fuel, supply of oxygen, that's air usually. And some miraculous, wonderful materials that are permeable to in this case, protons, hydrogen ions, because of an electrolyte that will transport the ions. This big image shows hydrogen coming in, giving up 2 electrons that go out to the external circuit, feed 2 protons into this electrolyte in the middle, migrating over in this direction where oxygen comes in and picks up 2 electrons, those 2 that went over, picks them up and splits into hydrogen ions and oxygen.
1/2 O2.
Half oxygen, that's all. There. Okay. So if you write those out, then as ordinary chemical notation, the anode over here, we have, it's oxidized, so it's a reduction that it promotes. The hydrogen gas gives up 2 electrons and feeds 2 protons into the electrolyte. That has an EMF. That there's a voltage across that junction, called junction potential. And I just write out as E0 H2 bar H plus just means we have those 2 phases in electrical contact. And then at the cathode, it's reduced, so it's an oxidizing agent. That's oxygen. It's a good oxidizing agent. Hydrogen is a good reducing agent. The reaction is a half mole of oxygen gains 2 electrons and reacts with 2 protons with 1 water. And it has an EMF, a junction, which I describe as E0O2/H plus. Some of them might get cell reaction. And that you can measure. You cannot measure these separately. You can measure the EMF of the cell. And our clever electrochemists have fancy potentiometers and methods of doing this. How do they get this result? So the EMF of that cell is the sum of the anode potential plus the cathode potential gives that value. And I just mentioned here that junction potentials can't be measured, but full cell EMFs can be. So arbitrarily, in order to be able to tabulate junction potentials, you have to have a reference to something, and the reference is the hydrogen cell, the hydrogen junction couple. And so this one we just say it's 0 by definition, which makes 3 energy just say H hydrogen ion equals hydrogen ion 0 as well. All right, so we've got the result there. So I'll show you the tabulation. The back of your book is a pretty good tabulation of these junction potentials. And they look something like this. These are called reduction potentials. Sometimes books write the equations the other direction, and then they're oxidation potentials, and they change the signs. So you gotta watch out what you do. I made a notation up there about that. Well, here's that one. This is the reference. Everything is referred to. This hydrogen junction we just talked about. And down here, we finally get to this one, which is the oxygen, acidic medium. And it says 1.23, but I've put out more specific pages because we want to calculate something for you for the table. That's what the measurements are. And you see lots of others. If you look at your textbook, you'll find a pretty good list of them. And the beauty is that you can pick any 2 of these and put them together, one anode, and turn the other one around, make it the cathode, sum them up, get a cell potential for the reaction that you get when you sum those together. And every reaction you can write down that way. You know the E0 for, you know the delta G0. That's pretty slow. So, for the reaction, hydrogen gas plus 1/2 oxygen gas goes to liquid water minus delta G0, E0, delta G0 is minus N delta T, and we know that E0, and we know that E0 is 1.2289 volts. Then delta G0 is minus. All right, what does this N stand for? It's the number of electrons in these equations up here, I wrote those for the one, remember that? I've written it out for two electrons that we have to, in these two. Doesn't change the voltage, it changes the free energy. Alright, so I'll just write, it's 1 mole of electron, that's what that stands for. Faraday constant is 96,485 coulombs. Let's use a capital C for it. That's the charge on 1 mole of electrons. So you take 1.602 times 10 to the minus 19 coulombs per electron will cause Avogadro number. You got that stuff. Drops out. And E0 is a K. There's 1.2289 volts. Oh, damn, this doesn't turn out to be minus 237.14 times 10 to the 3. And while we have, oh, and this is coulombs, excuse me, per mole. Right, so what's left over is volts times coulomb. Well, normally you want to tabulate these free energies in some useful energy measure, and what would that be? That's in joules. But what the hell is a joule? It's a volt coulomb. So you can say 1 joule per 1 volt coulomb. So it's minus 237.14 kilojoules per mole. That's double G0. There's no per mole on that. Okay. This, however, is equal to, as always, the summation of ui 0. That's equal to, looking back at the balance equation, 1 mole of water times U0 of water, minus 1 mole times U0 of hydrogen, minus 1/2 mole times U0 of oxygen. So what are these two here?
0.
0.
They are both zero. And so we solve for U0 of water is equal to delta G0. And that is equal to minus 237.14 kilojoules, and that's what we tabulate. So put a question mark in that table window. What is this? So how many values can we get into our extended table by this kind of process? Well, a few, but not nearly as many as might be of interest, because you can't make every reaction be the cell reaction of that cell. Impossible. So for those you can, you can get interest, and that's a method. I'll review this, or illustrate this with one of the calculations here. Example of determination of another UI0 using electrochemical cells. So if I went back to that, to those reduction potentials, I would find a couple that look like this. From the junction potential, tables, we get chlorine, gas, plus 2 electrons, goes to chloride, ion, aqueous. And we have E0 is 1.36 volts. And I got silver plus chloride, silver chloride solid. Oh, and also get and E0 is equal to 0.22 volts. And we sum those together, get the cell reaction, which is silver. And I'll just multiply this through by 2. Now that doesn't change the EMF itself, it changes the stoichiometry of the equation. So I get 2 silvers plus CO2, 2 silver chlorides, and the EMF standard cell is the sum of those 2 or 1. David now. Yeah. Alright. So writing it this direction, the EMF's on the other side. I took this out of the table because that one is mine, so I turn that one around. That works better. And then we got 1.14 volts. And delta G0 is minus delta D0.
Excuse me,
And,
Professor?
yes,
When you flip that around, don't the electrons go to the same side of the equation?
no, I flipped it around from the chart. So the charts are all reduction potential.
Oh, okay.
You gotta turn one of them around to make a cell. But I can find that chart, I can show you.
So that was original GCO plus electron. Okay.
That's right here.
Got it.
Right here. Okay?
Thank you.
So the tables are all either reduction potentials or oxidation potentials. So when you want to build a cell, you've got to use one of them, see written, and the other one, turn it around and reverse the sign. And I just haven't done that in my head. I've done it. All right. So that's minus enough. So that's equal to minus. Now what? What's F? Now it's 2, because that's how many electrons we were pulling. And it's still 96,485 coulombs per mole. And U0 now is 1.14 volts. And this turns out to be 220 kilojoules, not kilojoules for bleeding mole. Just kilojoules. What would be a mole of? Anyway, look at the equation. It's the change in free energy for an equation, not free energy of moles. Right, delta G0, this also equals summation of UI0. And that is equal to, for this reaction, it's 2 moles times U0 silver chloride minus 2 moles times U0 of chlorine gas minus U0 of silver. Silver minus 1 mole times U0 chlorine. Now what are these two down here? They are both
0.
0. so consequently we have U0 of silver chloride solid is equal to delta G0 over 2 moles. And you put that there, you get 1. Even if you write that minus sign there, you get minus 110 kilojoules per mole. And now you get flow in there. And tabulate that. Any questions about that? This is first board, not very exciting. I know, as I said earlier, not every change in state of interest can be studied and left to oneself. A lot of them can, not every. The vast majority can't. So we need other ways to get interest. Well, there are a couple of other ways, fortunately. They're based on applications of third law coverbacks, which we will now consider briefly. The time for a study third law, but we'll look at it enough to figure out how to use it to flesh out that table. The table is very useful, much more so than just small percent copies alone. Then you can calculate each of the reactions, which gets boring real fast. When you add the free energies, chemical potentials, you can calculate driving forces for reactions, you can calculate chemical equilibrium, lots of wonderful things. I won't be able to tell you about this, our time's running out, nonetheless, here we go. So, let's other than that, it's based on applications. Third law. Which we're going to explore a little bit. I'm not going to write the law out for you right now, like we normally do. I'm going to tell you some things about it, then we will write it out in 2 versions. Consider some familiar changes we have studied and know about. Some expansion of ideal gas. We know that delta S for isothermal expansion of ideal gas is NR1 V2OV1. Do I remember that? I need to remember this. And that it is greater than 0. We know that using the solid, the liquid, that delta S of fusion is equal to delta H of fusion over the temperature of fusion, and we know that this is greater than 0. I always have to put it in there. Fusion is an endothermic process. So that's great. We talked about evaporation. We saw that delta S of vaporization, delta H of vaporization, temperature of vaporization. This is always positive. We talked about delta S of ideal mixing. We saw that was minus R times the summation of Ni along with Xi. Because Xi's are less than 1, the logarithms are negative times negative. This is always positive. And there are others that like that. These are just some things we put down this. Well, thing these have in common, was noticed by scientists in the 19th century who were developing thermodynamics, thinking about it, especially by Boltzmann. One thing they have in common is that in each case, we're proceeding from a system in one state of order to a system in a more unordered state. The degradation of the quality in terms of orderliness of the system. Okay, so the evaporation, just think of free evaporation. Put a gas, ideal gas in a little box, vacuum over here, and open the chamber, it expands into the vacuum, it essentially goes up, right? About that amount. And what happens? Well, it's a lot more spread out now. It's state of what little order it had in this state is now spread out over larger. It's this state. You can't make it go back. It's an isolated system, it expands, and you can wait forever, and it's not going to go back. Degrade. Fusion of a solid. All the molecules sitting here are pretty much lined up, ranking 5. Passing inspection, happy as bugs. But you make them shake around, you warm it up to the melting point, finally they just let go and they just get sloppy and it's all out of ranks. It's disorderly. The liquid molecules have some mobility around. Big. There's disorder. Take the liquid or the solid, either one, and evaporate it. Now the molecules go completely off on their own and say the hell with you. And the disorder is just even more bigger change in entropy. Mix it. Crud A and crud B, let them come together, the molecules mix up, and surely that's a more disorderly state. Entropy goes up. So entropy seems to increase when systems proceed from relatively ordered states to less relatively ordered states. Perhaps entropy related to the order of the molecules, the parts making up the system. So one way to try to get a handle on this is to consider n identical coins. They have 2 states each. Either head or tails up. The number of ways to arrange in coins. In state where there's N, H heads and N P tails, so that N H plus N P is equal to N is what? Is what? Everybody know?
N
Numbers in here?
Is it n factorial?
Pardon?
N factorial?
I can't.
N factorial?
Oh, no. No, it's not in fact. Number of waves. They're just one. They're just one. How many ways can you have 3 heads and 1 tail? Well, they're just 4. How many ways can you have 2 heads and 2 tails? Count them, you write them all down. Turns out there's 6. And then you go back down the other way, it goes 4, then 1 again. 4. 1 head, 3 tails, 4 tails. Half for you. Well, the number, which I call omega, be this number. Make that figure arrangement. Then omega is equal to the n factorial divided by h factorial and p factorial. Makes difference. If you sum all these up, we have the sum of omega i's. You get 10, you get 16. So we have a probability of a distribution, 1/16 for all heads, for all tails. It's 4/16 for 1/4 for 3 heads and 1 tail, or 3 tails and 1 head. And it is the most probable distribution, 3's. Right, if we plot that out, plot out that distribution. We would have a 1 and a 4 and a 6 and a 4 and a 1. So where we're going with this, we want to apply these ideas to chemical systems. We want to apply them to atoms and molecules. How many of them are going to be? L.14. So let's push for that. Let's go up to 10. Here are 10 coins. Also outcomes. This represents the number of heads down here. Number of heads or number of tails. 1 head and 9 tails. No, excuse me, this right. Crazy.
Number of occurrences.
This is one way that you can have 10 heads. That's 10 ways you can have 1 head, 9 tails, 4 or 5 ways. So come to the highest, this is what? 5 and 5. 252 ways. Somewhere or another, I guess I have it here. Copy it myself. So the 250 ways for the most probable configuration, you sum them all up to 1,024. So the probability of the most probable distribution is 0.246. Probability of 1 in 99. 1 in 9 in this case is 0.976. What's happened to the distribution? It's gotten higher, gotten a little narrower. 10 to 20, a little over 10 to 29. You can see where this goes now, go with the Wagner numbers. You can see that and you can understand statistical mechanics. So it's about 10 to 29, about 10 to 30 total combinations. So the probability of the 50-50 distribution is whatever I said there. That doesn't look so much, but the probability of
1 head and 99 tails.
yeah. The probability of all being the same, it just zilch. All right. So what I want to tell you about this is that 1 milligram of gold. That's a real small sample. Has about 3 times 10 to the 18 atoms. Times 10 to the 18 coins, the most probable distribution, 50-50 split, most probable distribution. These factorials, those big numbers, are impossible to calculate. You can put most probable computer, but they can be approximated pretty nicely. There are various schemes for doing that. One Stirling's approximations. I'm not going to go through the mathematics of that with you, but it turns out that this is very, very nearly equal to this at the logarithm of omega, which is very nearly equal to n times the logarithm of 2. And this means that probability of the most probable 50-50 distribution turns out to be about 10 to the 9th. That's a big number. Times 10 to the 17th. Is that a big number? That's a long big number. That's a huge number. That's in the order of that's a billion. 17th power. That's bigger than even the dead of Greece or our national treasure. And if we plotted out the distribution, then we just here's the distribution at the it would be a virtual look like that. You could examine it real close, you'd see some fuzz on it. You see a little tail out here. Tiny. The virtual static motion. And atoms and molecules have a lot more than 2 states each. A whole lot more. So we talk about the number of ways you can arrange atoms and molecules to satisfy the conditions of a certain state. It is sometimes. But the most probable arrangement is more probable than all the others. And for most purposes, you could just ignore the others. Focus on the most probable. That's the beauty of statistical mechanics for large collections of things in chemistry. So, third law. statistical approach is to assume the entropy of a substance is proportional to omega, where omega is proportional to the probability of an arrangement consistent with the state of the system. In other words, if the molecules are in an arrangement consistent with that, then the properties are the state properties. Pressure, temperature, volume, melting factor. You change the state and you change that number. The probability is equal to probability of arrangement I is that over the sum of all probabilities. We don't ever calculate that. We just focus on the number of ways arrangements are made. You see why that is in a moment. We won't hear in a moment because it's out here in a moment. You see why that is tomorrow. Okay, so.
Mhm.